Bledsoe entipole method. The idea of the entipole method was select n pixels from an image, and this is mainly directed at visual patterns. And in the training, you record the entipole states. These are the values that occur in the training set. So for the letter T, and I think I gave you 3 examples of a letter T on a 3x3 array. So that would be a perfect 3x3 T. That would be a shorter 3x3 T, and one with a sloping horizontal bar. So that's equivalent of a T, that's equivalent of a T like that, and that's equivalent of a T like that. Now, if I were to take this very simple example, and if I was looking at the top row, this would be a 3 tuple, because it contains 3 pixels, and the states which would be allowable would be, in this case, black, 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 which is 1, 1, 1, which in decimal would be state 7. Would be 7. We've got 7 again. At this stage, we're not taking the frequency of occurrence into account. It's just whether the state has occurred or not. We've already got 7, so no action. And the final pattern gives me 6. So we have 2 allowable states on the top row. Repeating it as I did last week for the middle row, we also get 2 states. And for the bottom row, 2 states. The bottom row would be state 2 and state 0. Now, having got those states, we can test, and we will get a response if the state is allowable from the training set. So as long as I have a 7 or a 6 in the top row state, as long as I have a 2 or a 3 in the middle row, and as long as I have a 2 or a 0 in the bottom row, we will get a response. And this allows generalization, because the states do not have to occur in any single reference pattern. They can occur across the whole training set. So if I had, for example, a pattern that looks like this, and again, very low resolution, that I would say would be a sort of T with a wedge-shaped top, something like that. Okay, it might look a bit like an axe, but we're doing character recognition, so that is a T. This would give a response. The top row, 7, allowable state. The middle row, 3, yes, an allowable state. And the bottom row, 2, allowable state. That would give a response, and it is not a training pattern, so the system generalizes. So I want to leave the entipole method there, and we'll come back to that a bit later on. I now want to have a look at a digital model of a neuron. So back to the natural neuron. It is a blob of biology with a cell body. It has inputs, it has an output there, call that Z. These are the inputs, I1 to IN, and some function goes on in the cell body that relates the outputs to the inputs. Now, it is generally regarded that the information, well, it's known that the information on the inputs and the outputs are electrical voltages, and in general, we can identify two conditions on any line in or out of a neuron. The system is either, or the line is either firing or not firing. So if I were to take a voltage line, voltage against time, we might have a signal that looks like this. Then all of a sudden we get a spiky activity, then it's, and then spiky activity again, and so on. Two states. Sounds like logic to me. We could call this state 0 for not firing. We could call this state 1, 0, 1. So we can interpret the voltage signal as a binary signal. And just out of interest, the magnitude of the voltage on a nerve, that would be about 100 millivolts. So it is quite small. Right. If the inputs are binary, and if the outputs are binary, the question mark, what is the obvious thing that could link them? A logic function. So instead of having a vector model, which we were having with the analog neuron, we are now going to use a logic function. And if I go back to the example we used for the training of the analog neuron, the example, it should be back in your notes a couple of weeks ago. I think the patterns we were using were class 1, and the other pattern was and the other class we identified was, and won't bother with the box. It was those, and we called this the plus class, and we called this the minus class. Instead of having plus and minus as an analog value, which is thresholded in the output of the neuron, let this be the f equals 1 class, and let this be the f equals 0 class. It could be the other way around, but let's choose it as it is. Now, if I were to label the inputs as variables, let's call that A, B, C, and D, the logic function that will respond to these two patterns is going to be F equals A, B, not C, not D, or A, not B, C, D. Okay, now that will immediately respond to these two patterns, F equals 1. These aren't in the F equals 1 terms, they're noughts on the truth table, they're not the ones, so they must be naught. It will also respond to these two patterns. It will discriminate between the 4 patterns that we are looking at. But a problem. The system does not generalize. It will only recognize the patterns that it's been trained on. Now, we could take the other terms. There's 4 terms in the training set. If it was a truth table, we'd have 1, 2, 3, 4 terms out of the 16 possible terms of a 4-input function. The other 12 terms cannot be regarded as don't cares because they could contain the important patterns that belong to these 2 classes that aren't in the training set. And if a system doesn't generalize, it isn't going to be of any use in real data. So, given that a logic function does not generalize, we've got to think of an improved structure to include the property of generalization. And this is where we can get some inspiration from the Browning and Bledsoe method. Now, the other important thing, if we're thinking of Browning and Bledsoe methods, you have to search the lists of allowable states for each interval for each class. If you have a logic function, there is no searching. You get a response from the logic in nanoseconds, which will tell you f equals 1, it's a member of the allowable set, f equals 0, it is not. So this becomes a parallel access of what were the allowable state lists in the Browning and Bledsoe. So let's expand this structure. And I'll concentrate on a 3x3 example.
I've just got one question.
Yeah.
The thing we've just done then, I thought that did generalize because when you make the decision surface, you run a test pattern through it and then it tells you which side of the decision surface it goes on. I thought that was the definition of generalization.
No.
Could you explain where I've got that wrong?
These are the training patterns. These are known patterns we're using to try and get a function to separate whatever these 2 classes were. Now, with the weighted function, it will put a decision surface, which is going to be a hyperplane, and it will generalize, as you saw from the previous example. If, however, I was using this logic function, it would only respond to this term, which is 1, 1, 0, 1, or this term, which is 1, 0, 1, 1, which are the scanned versions of these patterns, 1, 1, 0, 1, 1, 0, 1, 1. It will only recognize those 2 patterns, f equals 1. It will not recognize patterns outside. Okay, the Browning and Bledsoe does, because it's got allowable states at each interval sample. Right, let's now go to a 3x3. Was I writing that down? Yes, a 3x3 structure. And I am going to take 3 logic functions. So these are going to be logic. And I'm going to use a 3 tuple, so we will have 3 inputs to each function. Let's have a summation coming out. And follow that with a threshold, the same as we have for the other nets. Right, and this is the input. And we now have to define a connection which determines the sampling of this input pattern, usually random, but so it's easy to see what's going on and follow. I am going to use a linear mapping, and I am going to connect the first one to the top row. Go away. The second one to the middle row, and the third one to the bottom row. So this is the mapping. And it is row by row. Just for this example, real life, it would be random. So these are going to be the inputs. Right. Training. Let's take the T example again we used in Browning and Bledsoe. There is the perfect T, that's training pattern 1. Here is the short and vertical, there is training pattern 2 and the sloping top, training pattern 3. Now, this function, to respond to the allowable states in this training set, it has to be state 7 and state 6. So F1, F2, and F3. F1 is going to be, in shorthand notation, 6, 7. First canonical form. F2 is going to be 2 and 3. I hope you remember this notation from level 1. And F3 is going to be 0 and 2. Right, now this sort of idea came about, again, a long time ago, round about the 1970s. And at that time, there was no such thing as programmable logic. You actually built the circuits up using AND gates, OR gates, NOT gates, or of course NOR gates if you were a smart logic designer. And each time you changed the function, you had to change the circuit. Now, one important property of the logic function, F1 initially equals A and B and C. That will respond to the n tuple from this pattern there. If, however, I add a different state here, for example, this state, that will give me the term A and B and not C. The logic function does not lose the response to 1, 1, 1. You're changing the logic function, but you are retaining the response from earlier patterns. Now, that is in complete contrast to changing a weight in an analog neural network, where if I change the weight for this function, I may well introduce an error here. So the logic functions are additive. And this leads to a hugely important property of these networks. The training is only one pass through training data. There is no recursive training needed. So instead of taking hours, days, or even weeks to train an analog neuron, if you're using logical models, the training is done at the microsecond level, one pass through a logic function. Now, implementing the logic functions. We are going to use random access memories. Now, again, when this idea was first proposed, we didn't have RAMs, so a special device called a SLAM was produced, which stood for Stored Logic Adaptive Microcircuits. It was essentially a RAM, but at the time we didn't realize it was. So what we need to do for the logic function is take an 8-bit memory. The inputs, which are going to be the n tuple, is actually the address to the memory. And the output is F, and essentially this will be 8 storage devices, divided into 8. So, and the address, I'll write the addresses above it, 0, 0, 0, 0, 0, 1 through to 1, 1, 1. It is 8 bits of memory. It is always 8 bits of memory. It doesn't increase or decrease. Now, to put this function into this memory. I need initially assume the memory is all reset, all the locations are 0. I need location ABC 111 to be set to 1. I need A, B, and not C, which is 110, which is location 6, to be set to 1. All the other locations are 0. So there is my implementation of that logic function. And if I were to add another term to the function, supposing I wanted not A, not B, not C, this location would be set to 1. And again, we do not lose the previously trained information. And the other key thing is, and people make this mistake, we are using memories, but these memories are not being used as storage locations. We are not storing the pattern data. The entable is never stored. It is the response to the entable. The entable provides the address, it accesses the location, and the content says, yes, this is an allowable state, or no, it isn't. So the complete system for the T detector using this model here are my devices. I can now draw them as memories. Again, each 8 bits. Those locations addresses 000 to 111. And let's put a letter T on there. And it is row by row. I won't draw all the connections in. Let's assume it's row by row mapping. And n equals 3. Here are the outputs. So we've got F1, F2, and F3. For the 3T patterns, I won't draw them again, but you should have them in your notes. We've done the function for the first one. It is 7 and 6. So there is the trained function. For the middle one, we had 2 and 3, 0, 1, 2, and 3. All the other locations are 0. And for the bottom row, it was state 2 and 0. 0, 0, 1, 2. All the other locations are 0. Put in the summer. Put in the threshold. And let's set T. What's happened? Go back. Set the threshold T. It can be anything between 0 and, in this case, 3. Or in the general case, n, where n is the number of pixels. And little n is the entable side, n over n. So that is the structure. It's parallel. It's fast. It only needs a single pass in training. So, what is happening to the behavior of this system? Pattern space diagram. Again, I'm going to try and give a set representation rather than a graph. This is a Venn diagram, if you like. This is the universe of patterns. And for a 3 by 3 by 1 bits per pixel, there is going to be 2 to the 9 patterns. So that is 512 points in this space. Now for the T detector, we took 3 patterns. Those are the training set, and it represents a set in that universe. And let's call this TT, the training set. Now, on the 3x3 space, you as a human can look at all of those 512 patterns, and you could decide which ones can be recognized, which ones actually look like T's. So we have the data set. Let's draw that in there, which is the set which represents all possible T's. And let's call that DT, the data set. Now, depending on training and the nature of the patterns and other parameters of the system, a trained network, having been trained on 3 patterns, will always recognize those 3, but it will generalize to others. So it will have a generalization set. Let's choose blue there, which is the generalization set, GT. And if the system is going to work and earn us money and solve problems, ideally, GT, the generalization set, should be equal to DT. If those 2 sets can be made the same, the problem has been solved. Now, this behavior is cluster-based. In training, we grow clusters which try and match the data set. The training set gives rise to a generalization set. If that matches the data set, boom, we've solved the problem. Now, that is completely a different approach from the hyperplane, where in the analog net, for the very first training pattern, we divide the universe into 2, and we try and adjust that plane to have the classes on one side or another. This is much more flexible, and it's easy to control, and it is faster. So it is cluster-based, no hyperplanes. So, what are the parameters of, first of all, the universe? Just comment on the universe. Don't be fooled by these simple square boxes. They are big. Three by 3, the number of points in the universe is going to be 2 to the 9, 512. If I go to 4 by 4, U is going to be equal to 2 to the 16, which I think is 32,000, is it? Or 16,000. What's 2 to the 16? Somebody work it out quickly for me. 2 to the 10, it's 32,000-ish. If I go to a practical size, which is pretty low resolution, 16 by 16, U is going to be equal to 2 to the 256, and that is going to be approximately equal to 10 to the 80. So the universe is huge. So going back to this set diagram, the way I've drawn it, this set tends to occupy a lot of the space, but U is bigger than shown in the diagram, and we can have hundreds, thousands, and millions of clusters within a practical universe. Right. Exciting idea. At least I think so. What are the parameters now of the logical network?
I've just got a quick question about the generalized set.
Yes.
Is it correct to say that the training set is within the generalized set?
The training set is always within the generalization set. And you
Right.
never lose the response once the network has been trained on the training patterns. They are fixed. Great.
Okay.
Okay. Right. Parameters of the logical net. And the first one I want to look at, and I've spent a bit of time on this, is the mapping. If you go back to the diagram, that's the one I had there. If this was a McCulloch-Pitts neuron, the function would have a connection to all the points. So this would be a 9-input vector, and it would go to the neuron. We are subdividing the space into n-tuple samples, and they are independent. The number of ways of connecting this, I've connected 3 by 3, but taking this first one here, 9 pixels, I have 9 choices for the first sample here. I will have 8 chances for the choices for the second one. I will have 7 for the third. I will have 6 for the fourth. The number of mappings we can get, the number of different structures, the number of total mappings is 2 to the n. So if I go to a realistic 16 by 16, again, a huge number of different ways of connecting these systems up. And again, it ties in with biology. All our neural networks are randomly connected. We never share the same system, but we can all perform in a similar way. So that's another interesting feature. But to show you that the way the network is connected will change the behavior of the network, I want to take an example and try and get the idea over by an example. And I want to use a vertical bar detector. And the training set I want to use is patterns that look like a vertical bar. And that's a pretty good vertical bar. Training pattern 1. If I have training pattern 2, there is a vertical bar displaced to the left. Taking the third pattern, the vertical bar displaced to the right. Now, if this is the training set, where have you gone to? Oh, it was going so well. I've lost my whiteboard. Ah!
Sir, shall I try and take control and zoom it to the right place?
Can you? That would be great.
I can. I'll request control. I've pressed request control, so I think you can approve me from your side.
Now, where do I do that? I've got my Teams front page up.
I'm not too sure, actually.
Yeah. I've lost my whiteboard completely now. Oh. Are we back? No, it's not writing. Give. Oh, this is an awkward thing to use. I've lost my whiteboard. Folks, I'll talk you through the training and make notes from my what I'm saying and see if you can follow what's happening. The three training patterns we had was the vertical bar on the left, the vertical bar in the middle, and the vertical bar on the right. Okay, we're sampling these patterns row by row. So the interval size is 3. We're looking at the top row, we're looking at the middle row, and we're the second pattern top row and the third pattern top row. And looking at that, if I were to write the logic function down, there would be f equals, from the first pattern, term 4, for the second pattern, term 2, and for the third pattern, term 1. Okay. Now, that is exactly the same pattern for F2 and F3. Now, if I have a threshold, let's set the threshold of t equals 3. I want a response from every state. So the pattern.
Sorry, John.
Yeah.
I think you've just zoomed out. If you zoom in, because you're currently at 0%, if you zoom in so you're at 100%, because I can still kind of see the work. It's just very zoomed out.
No, it's not wanting to do it.
Sir, just press Control and the plus key on the keyboard to zoom in.
No, I've lost it. Oh, this is. Right, folks, I think I'm not going to have enough time to go through the example I wanted to do. So are there any questions you'd like to ask me on this new idea of using logic functions as models of a neuron? The key thing to realize is the training. The training is additive. Very different from putting a weight vector which defines a decision surface. Because when you're using the analog network, you just train on one pattern and you've got 50% of the universe generalized in one class, the plus, and 50% in the other side. With the logic function, if you train on one pattern, it will only respond to that one pattern. Similar to the Browning and Bledsoe, if you had one training pattern, it would be simply a mask matching, comparing the patterns, the training pattern with the unknown, a perfect match, and the training is the unknown. When you start to have variations and more than one state at the sampling point, you have a choice. And if you take a situation where I've got 2 states in the top row, 2 in the middle, and 2 in the bottom, then when I test an unknown pattern, if the top row is one of 2 choices, the middle row of one of 2 choices, and the bottom row one of 2 choices, the number of combinations is 2 to the 3. So going back to my generalization set, I started off with 3 patterns in the training set, the generalization set, 2 states on each sample, 2 to the 3, the generalization set is 8 patterns. And that is the way the system generalizes. And of course, it works. The training is at electronic speeds. So these are some of the advantages of this particular approach. Okay, it's 5 to 12 now, so it's really the end of the lecture. I'll try and sort out the whiteboard next week. I am giving one more lecture, and then it's the Christmas break. And I do hope it'll be possible to have some face-to-face teaching next term, but we shall see. Any other points?
I think that's everything. Thank you.
Okay. I am in campus most Mondays, so if anybody wants to do a face-to-face with all precautions and social distancing and masking, we're quite happy to do it outside or in a common area in the university. And hopefully next term will be somewhat easier to meet up. Okay, folks. Have a good week.
Bye.
Thank you.
Bye for now.
Bye.
John,
Yes.
is it okay if you just try to press Control and scroll in to see if it zooms in? I just want to see if that works. So if you click on your
Control.
do you see the grey thing that's appearing on your screen right now
Yes.
at the top? I'm requesting Control.
You're Mustafa, are you?
Yeah,
Yeah, okay, allow.
sure. So I'm clicking this and I'm going to yeah, it's a bit weird.
Your pointer's going all over the place. Settings have come up.
Can you try pinch the screen like inwards? Yeah, so you're zooming in and zooming out to the percentage.
It's going down. It's zooming in.
Yeah, but I don't think that works.
It's not working. It's
Yeah, I can't see the work clearly, but sure. Maybe the works here.
yeah. It's not a very robust system, I'm afraid. It's coming back in.
So now I'm scrolling.
Yeah.
Are you pinching the screen as well?
Not at the moment, no. I'm not touching it.
Okay, so if you scroll in and out, then it zooms in and out.
Yeah.
So that's how it works.
Yeah, but it suddenly I must have touched something. It suddenly went, didn't it? Right. Yes, this is today's lecture coming up. I'm scrolling up now. Okay, we'll try and see how it goes next week. Thanks for your help, Mustafa.
You're welcome, John.
Have a good week.